Okay, so next topic is power dividers and couplers. So whatever we use at microwave frequencies, so similar concept we can extend to millimeter wave frequencies. So only thing is that we have to do frequency scaling of the components, and also we need to keep in mind about the losses. So let's start with a simple T junction. Frequently we use this junction to feed antennas, particularly antenna arrays. It is shown in microstrip line form and CPW form. So we have port P1. From this, power is divided into port P2 and port P3. So in right hand side figure, the same thing, from P1 it is fed to port P2 and P3. In the right hand side you can see these black lines, they represents wire bonding to keep the ground plane at same potential. If you remember that even odd mode problem, we don't expect even mode excitation, because even mode it radiates in CPW lines. We only want the odd mode odd symmetry. So for this we are using this wire bonding to keep the ground plane at same potential. Now in transmission line form, then we can represent this port P2 and port P3 by using two different transmission lines at the input impedance as seen by port P1. Then it becomes the parallel combination of the impedances of port P2 and port P3, or we can write down y in this is equal to 1 by z naught for port 1 equal to 1 by z1 plus 1 by z2. Now if z naught is 50 ohm, in that case if I want equal power split between this port P2 and port P3, we should have z1 equal to z2, and not only that, 1 by z1 plus 1 by z2, that should be equal to 1 by 50. So z1 and z2 each should be 100 ohm. Now let us say left hand side we have 50 ohm system, right hand side also we have 50 ohm systems. So in that case, how to modify this circuit? We can use lambda g by 4 impedance transformer, quarter wave impedance transformer. So we have to connect two impedance transformers, one between port 1 and port 2, another one between port 1 and port 3, and the characteristics impedance of this impedance transformer, it should be then square root of z0 into z1 for port 2 and square root of z0 into z2 for port 3. So for 50 ohm systems, for all these three, then the characteristics impedance of the impedance transformers, it comes square root of 50 into 100, approximately 70.71 ohm, and the length at a given operating frequency, let us say 60 gigahertz, the length should be lambda g by 4, where lambda g is the guided wavelength. But the problem with this T junction power divider is that port P2 and P3, they are not isolated. So if there is any reflection, let us say from port P2, that power will come back to not only port P1 into port P3 also. So this is the problem with this T junction. Then how we can modify it? We can modify it by using a resistor, and the modified form is Wilkinson power divider. So you can see here, although it is showing on microwave design at lower frequencies, same principle we use at higher frequencies, millimeter wave. So left hand side we have 50 ohm systems, we have two impedance transformer, they form one rectangle, and in between we have a resistor of 100 ohm, and right hand side we have port P2 and P3, they are again terminated in 50 ohms. And this is the measured response of this Wilkinson power divider. You can see S11 input impedance matching from port 1, it's quite good. S21 is equal to S31 and they are approximately minus 3 dB. It shows equal power split. And isolation S32, it is also down. At the operating frequency, it's below 40 dB. We have good isolations. So ideally, what should be the S parameters of one Wilkinson power divider? From all the ports, we should have 0 reflection. That means S11, S22, S33, they should be 0. From port 1 to port 2 and from port 1 to port 3 and its and vice versa, they should be equal, but we have a change of phase 90 degree, but this phase difference is same for both this port. That means angle of S21 is equal to minus 90 as well as angle of S31, that is again minus 90, so that we do not have any phase difference between these two output ports. So this is one basic property of power divider. We do not have any phase difference between the output ports. Now let me show you some millimeter wave circuits. So this is showing one T junction realized in CPW technology at 94 gigahertz on silicon wafer. So left hand side, this is port P1 and right hand side port P2 and P3. You can see the impedance transformer lambda G by 4. We have different signal line width. In this middle part, it's having 70.7 ohm characteristics impedance. For that, signal line width is smaller and the slot width is higher. And you can see a photograph is given here of the fabricated structure. So for this one, these black lines, they actually are showing the wire bonding to keep all the grounds at same potential. Now when we design something at so high frequencies like 94 gigahertz, we have to be very careful about the bends and junction. They are always associated with some inductance and capacitance. So for this example, right hand side, we are using a corner bend, and this bend, it is associated with some inductance and capacitor. Usually it is represented by a low pass T network, 2 series inductors and 1 shunt capacitor. So we have to nullify the effect, and for that we need some sort of reactive compensation. You can use any full wave simulator to determine the exact dimension of this reactive compensation. So you can see for this bend, intentionally the characteristics impedance of this bent section, it's quite high to nullify that low pass filtering effect. And not only that, this bend, it can generate higher order modes. For CPW line, it can generate even mode. So again we are using wire via or wire. You can see in right hand side photograph, these black lines, they are showing the wire bonding to keep the ground planes at same potential. Similarly, we can also design Wilkinson power divider on silicon. Now for Wilkinson power divider unequal power division, that is also possible. In that case, we have to use these design equations. For example, if the power ratio between the ports P3 and P2, they are given by k square equal to P3 by P2, then the design equations for Z03 and Z02, they are given by these two equations, and the required resistance in this case, it is not 100 ohm, but given by R equal to Z0 into K plus 1 by K. Here is one example of 1:8 Wilkinson power divider. If you look inside, it comes in PCB form with packaging. This is the input port. It is first divided into 2 ports using one single Wilkinson power divider. Then it is divided into 2, and finally we have 8 output ports. We can also design wideband Wilkinson power divider. For this is a very standard technique for bandwidth enhancement of any couplers and power divider, that you use multiple of the components, but obviously in that case design equations will be different. So, here is one example. It shows a 3-section wideband Wilkinson power divider. So, you can see it is in microstrip line technology, and the thickness of these strips of different sections, they are different. This is one example of a Wilkinson power divider at 94 gigahertz designed on silicon. So, we have many reactive compensation along with the wire bonding, and this black dot, it represents the resistor. Usually we use thin film nickel chromium resistor at high frequency, millimeter wave frequencies. So, this is typically it shows a loss of 0.4 dB, which is considered a very good value at 94 gigahertz. So, loss 0.4 dB, that means instead of S21 equal to -3, we are having S21 equal to -3.4 dB. S31 is equal to -3.4 dB. So, next we will go to coupler. We can design couplers in microstrip line technology as well as using any other waveguiding system like rectangular waveguide, image guide. In all the guiding systems we can design couplers. Let me give the first example in image guide, where we will consider two coupled image guide. They are parallel to each other as shown in this figure. So, if you recall, we may have TM to Y and TE to Y mode, and just like microstrip line, we can divide for analysis. We can consider the even mode excitation and the odd mode excitation scheme. In even mode excitation, this is the plot of EY along X. So, EY, it is maximum on the inside the image guide, and it is having minimum value in between two. So, if you remember, for the microstrip line case, we can use one PMC between these two coupled lines. Here also almost similar thing, and for the EY variation in odd mode, they have positive and negative value for left and right hand side. So, coupling, it can be controlled by tuning the gap between two guides as well as length of this coupled line. So, this is showing a typical top view of a directional coupler using image guide. Now, for practical realization, as I said, whenever we design any band, we have to be very careful. Each and every band, it is associated with some reactance, and at lower microwave frequencies usually we do not consider its effect is negligibly small, but if we go for high frequency design, typically above 60 gigahertz, we have to consider their effect. So, you can use any full wave simulator to characterize and to minimize this reactive loading effect. For this example, we are showing different types of termination. So, from this coupled section, how we are dividing power among this port V1 to P4. For the first one, we are using a straight junction. For the second one, we are using a rounded junction. The rounded junction, it shows somewhat improvement in terms of bandwidth. Then the overall S21 and S31, they can be represented in cosinusoidal and sinusoidal form. It is cos pi LF by twice L. So, where capital L, it is equal to pi by beta E minus beta naught. So, beta E and beta naught, they represents the phase constant for even mode and odd mode excitation, and LF, this is the effective couple length, and this is L naught plus some we have correction factor. So, this correction factor is because of this bend actually. So, L naught you can see this is the straight part, straight coupled part, and in addition to that, due to this bending, we have to add some correction factor. So, this is twice L by pi into delta phi, where delta phi this is we integration z1 to z2 beta e minus beta naught over dz. But the problem of this coupler that the bandwidth is very small, typically 3% or even less than that, but wideband coupler multi sections and using some sort of inset wideband design is possible, and the effective coupling length it decreases for a broadside couple structure. Here we are using side by side couple structure. So, if one is above another one, in that case we have higher coupling level. I am showing you another example here. Port 1 and port 2 they are in microstrip line technology, whereas port 3 and port 4 they are in image guide technology. So, this particular coupler it involves two different types of transmission line system, wave guiding systems, and now the coupling it is being controlled by some slots etched in the common ground plane. So, on top we have microstrip line, and below the ground plane we have the image guide, and now by controlling the diameter of this slot and the position of the slot, we can control the coupling level. So, it is usually very wideband and compact. Quasi TEM mode of microstrip line it is coupled to TM to Y mode of the image guide. So, for TM to Y mode, if you remember, so for a transfer TM to Y we have the highest EY component which is perpendicular to this ground on near the ground, and also we have a component along Z inside the image guide which has highest value on dielectric air interface. So, then from microstrip line mainly from this perpendicular electric field to this perpendicular EY component, this power is coupled through the slot in between this image guide and the dielectric of the microstrip line. Now, direction coupler in microstrip line technology. So, in this example, in the first example we are using simply a coupled microstrip line. So, in this figure right hand side you can see this is the main line, with this we have a coupled microstrip line here. In general directional coupler it is a 4 port network. Port 1 it shows the input port, port 2 we called it through port, port 3 is the coupled port, and port 4 is the isolated port. So, if we feed at port 1, most of the power it will appear at the through port, and a fraction of the power it will appear at the coupled port. Usually the phase difference between through and coupled port is 90 degree, and not only that we have some other types of coupler. For directional coupler, the power coupled to the coupled port is quite small, sometimes it is 10 dB or 20 dB down in comparison to through port, and they are typically used to monitor the power level. Let us say you are transmitting through one antenna and you want to monitor the power level. In that case we can use one direction coupler, and they also have some other uses. Some parameters, important parameters like coupling C. We define coupling C as 10 log P1 by P3 in dB, where P1 this is the incident power, P3 this is the coupled power available at port P3. Similarly, we can define directivity. So, isolated, how isolated it is with respect to the power coupled to coupled port. So, it is defined by 10 log P3 by P4 in dB, and then the isolation 10 log P1 by P4 in dB. For a lossless system it can be shown that I this is equal to d plus c in dB. That means the isolation in dB scale, that is equal to directivity plus coupling. And now for ideal coupler, then all these port they should be properly matched, or the input reflections it should be 0. So, S11, S22, S33, S44 all should be 0. Not only that, for ideal isolation again S41 it also should be 0. So, not only in microstrip line technology, already we have seen that it can be designed in image guide, it also can be designed in NRD, it also can be designed in rectangular waveguide technology. So, for this particular example, it is showing the 3 ports and the isolated ports actually terminated inside, and from outside you can only see 3 ports of this 4 port directional coupler in waveguide technology. Now, in case if we need higher coupling level, so as I said that usually for microstrip line or other directional coupler, power available at coupled port it is quite small, typically 10 or 20 dB down compared to through port. Now, in case let us say we need equal power splitting between the coupled port and the through port. So, what determines this coupling level? For microstrip line, that gap between 2 lines it determines the coupling level. If we decrease the gap, then coupled power will increase. Now, for equal power splitting, sometimes the gap requirement is so small that simply it can't be fabricable. So, in that case we have an alternative, that is called Lange coupler. So, instead of one section, multiple sections are used as shown here, and then they are wire bonded, so that the effective coupling between 2 lines it increases. So, this figure shows a typical Lange coupler to increase the coupling level. Next is hybrid coupler. So, in the previous example, typically they are used for very low coupled power. Now, for equal power splitting we prefer hybrid couplers, and hybrid couplers they do not involve any gap. Usually we use properties of transmission line to obtain that coupling criteria, and in addition to that we can add some phase requirements. For example, the output power between the output through port and coupled port, let us say we need a phase difference sometimes 0 degree, sometimes let us say we need 90 degree, sometimes let us say we need 180 degree depending on applications, and we can design all of them by using hybrid couplers. So, the first example is a branch line coupler as we call it. You can see again they are 4 port couplers. Port P1 this is the input port, port P2 and P3 they are the output ports, P4 this is the isolated port. And for conventional design, power incident at port P1 it will be equally divided between port P2 and port P3, and there will be one phase difference of 90 degree between port P2 and port P3. If we have equal power splitting, in that case if we solve using the required criteria of S parameters, in that case it can be shown the length of each arm at resonance frequency it should be lambda g by 4, where lambda g is the guided wavelength, and not only that, the characteristics impedance of this top and bottom line that should be z naught by root 2. This is for equal power split. So, for z naught equal to 50 ohm, then it should be 35.35 ohm, and left and right branch they should be of 50 ohm z naught. So, if we feed a power at port P1, then S21 angle of S21 it is actually minus 90, angle of S31 that is minus 180, and overall we have a phase difference of minus 180 minus plus 90. So, we have a 90 degree phase difference between port 2 and port P3. Next example is rat race coupler. Rat race coupler, it is very useful in radar applications. These have interesting features. This one. So, if you feed at port P1, you see port ejection is little different than the branch line coupler because of its property. If I feed at port P1, then power it is divided equally into port P2 and port P3, and port P4 will be isolated. So, the farthest port is isolated, and not only that, if you use port P1 as the incident port, then port P2 and P3 they will be in same phase. So, angle of S21 is equal to angle of S31. Now, if I use port 4 as the incident port, in that case again power will be divided between port 3 and port 2, but this time there would be a phase difference, and that is minus 180 degree. So, port 1 and port 4, any one of them can be used as the input port, but we have two different phase relationships. Now, if we use the output ports, for example, port 2 and port 3 as the input port together, so we have let us say a power source and we are feeding to both port 2 and port 3, then their addition will appear at, or summation will appear at port P1. So, that is why sometimes we call this one as the sum port, and their difference it will appear at port P4. So, we call it sometimes the difference port or delta port. So, that means if we have two signals, we can simply do their addition and subtraction by using a rat race coupler. So, this is the S matrix for one ideal lossless rat race coupler. Ideally, all 4 ports should be matched. So, S11, 22, 33, 44, all the diagonal elements they are 0, and you can see S12 and S13 they are 1 multiplied by minus j by root 2. So, power is equally divided with the same phase. Now, you consider for example, S42 and 43, we have minus 1 and plus 1 and multiplied by minus j by root 2. So, magnitude is same, but phase they are out of phase. Now, in this conventional design, I have discussed about equal power split, unequal power split also possible. So, in that case we have to derive the corresponding equations, and then the impedance requirement it will be different. For a conventional rat race coupler, if we do analysis for equal power split, then the arm length it is lambda g by 4. This longest arm length, this is 3 lambda g by 4. So, altogether it has a circumferential length of 3 into lambda g by 4 plus 3 into lambda g by 4 for this bottom part, and the characteristics impedance of this line it is uniform throughout, and it is given by root 2 multiplied by z naught. So, it is 70.71 ohm. This is using transmission line theory. Now, how we do analysis of this? We simply use even odd mode analysis technique. So, I will skip the analysis technique, just I am showing the first step. What we have to find out? We have to find out the even mode and odd mode equivalent circuit of this. Then we obtain the ABCD matrix, equivalent ABCD matrix in even mode condition and in odd mode condition. So, if you look at the circuit, we can place the symmetrical, we have to find out a plane of symmetry first. So, the symmetrical plane it bisects the coupler, and port 1, 2 will be at one side, 3 and 4 will be at another side. So, in even mode condition, this plane it will be replaced by PMC or open circuit condition. In odd mode condition, this plane will be replaced by a PEC or short circuit condition. Then we have the corresponding equivalent circuit as shown in here. Now, it looks like a simple transmission line and two open circuited stub, right hand side, two short circuited stub. We can obtain theoretically what is the S21, S11 for this given two port network. So, by using even mode and odd mode equivalent circuit, we can actually simplify a 4-port network to 2-port system. Then we do the analysis, find out the ABCD parameters in even mode and odd mode, then find out what is the overall reflection coefficient, transmission coefficient both in even mode condition and odd mode condition. Then we impose the rat race condition, that means this matrix basically S11 should be 0, S22 should be 0, and all these equal power splitting condition, phase difference condition. If we impose those conditions, then finally we have the design equations. So, we have basically two equations, and this is the general solution, and that means here we assume that theta 1 it can be arbitrary, anything, not just 90 degree, and 90 degree it is a special case. From this equation, if you put theta 1 is equal to theta 2 equal to 90 degree, in that case you will find out that Z equal to 70.71 for a 50 ohm system. So, we will take a break, then we will discuss about termination and transition. Thank you.